So this is a video that is designed to help you navigate your way around SPSS when you do unrelated ANOVA or between participants analysis of variance, and we're going to cover examples from the lecture number 7, which basically was analysis of variance revision session, as we expect you to know analysis of variance from undergraduate degree. So we're going to look at our first example, and basically what we have is a study where an experimenter investigated performance on perceptual motor task in 4 different experimental conditions. 24 participants were used in total, with 6 different participants being allocated to each of the 4 conditions A, B, C, D. Performance was measured as the percentage of the maximum possible score each participant achieved. The data collected are recorded below. So from this example, we can see that each participant took part only in one condition. So their errors do not correlate. So therefore, they're called unrelated ANOVA. So to get this particular data set, you'll go to the website where we have the link to all our articles and data sets, and it's called P in the brackets 8 example from the lecture. You press an arrow, download the file. I already downloaded it, so here it is. We have our scores and our condition. This is the main sort of data view where you can see all your data. In the variable view window, if you want, you can check how your variables are coded, how they're recoded, whether they have decimal places or not. So you can make any adjustment to your variable you want. So we know score is the scale measure. We record it in the percentages. It's not nominal, it's not ordinal data, it's a scale. So in the conditions, we have it as a nominal data. So the number that we assign to the condition corresponds to the name of the condition. And in here you can see how they're coded. So 1 equals group A, 2 corresponds to group B, 3 corresponds to group C. It's basically knowing this number, you would know which group participant belonged to. So going back to our data view, this particular example has one factor with 4 levels. And because it has only one factor, we can run a one-way ANOVA. So you can go to Analyze, Compare Means, and here is your one-way ANOVA. This option you can use only for unrelated ANOVA. So here we can choose well, let's just reset. Percent of maximum correct scores will go to the dependent list, condition will go to the factor list. And here you can also choose options and always choose descriptive statistics. We run them by default. You can run them separately through like analyze descriptive statistics and there choose means and standard deviations. But all tests of analysis of variance have descriptive statistics option. So we can choose homogeneity of variance test, which would test one of our assumptions for running F tests, that the population variances must be equal for each level of the factor. So this homogeneity of variance test will give you whether they equal or not. We can choose means plot, which will just basically plot the means in the graph and gives us a visual presentation of our data. Continue. In post hoc tests, you can choose to run post hoc tests on your data to determine where significance lies, but we won't cover it now. So press OK, and here is your output. So first table is descriptive table. It gives you mean and standard deviation for every single condition, as well as number of participants in each condition, or in each group in our case. It also gives you confidence intervals of the mean, and the easiest way of looking at it is that with 95% of confidence we can say that the mean of group A will lie between 58.5 and 69.2. We're not currently reporting confidence intervals for the means, but if you're requested if you asked to do that, then here where you look for your confidence intervals for the mean. Homogeneity test for testing our assumption is non-significant, and that's what we want, but we already could predict that Levene's statistics will not be significant from looking at our standard deviation, because it tests the equality of variances, and variance is the square root of standard deviation, so standard deviation squared is the variance. So very straightforward. The Levene's test non-significant, we are happy, so our assumptions are met and we can run the analysis safely. So this is the main ANOVA output. We have between groups, which is our main effect for the factor group, and we can see that it's significant. Within groups refers to error. And this is one of the confusions coming when you run your analysis through Oneway ANOVA, is that it will give you between groups and within groups. So you just need to know that in Oneway ANOVA, when you run it in SPSS, within groups actually represents an error term. So when you report your findings, the things you need to report is degrees of freedom for your main effect, degrees of freedom for error, F value, and then say if it's significant or not. So in this case it's significant. This is the mean presentation, this is the graphical presentation of your means. So you have mean of group 1, mean of group mean of group A, mean of group B, mean of group C, mean of group D. So just looking at this plot, you pretty much can assume that it's possible that group A and group C are significantly different, and group B and group D not really different, and A is probably also different to group D. But to know where exactly difference lies, you need to run a post-hoc tests, or you can run t-tests with the Benferroni adjustments. So the further analysis needs to be done in order for you to say which groups are different from each other. But in here, ANOVA just tells us that there is overall difference. It doesn't tell us where. So this is the output when you run one-way analysis. If you choose to run one-way analysis through general linear models options, and this is general linear model option, is where you find all the ANOVAs analysis. So you have univariate for unrelated ANOVAs, you have repeated measures for repeated ANOVA, you also run multivariate analysis through here. So we'll run univariate tests, and we have our dependent variable and independent box. Our condition goes into the fixed factors. Most of the time when you run research and analyze your data, your factors will go into the fixed factors. The main difference between fixed factors and the random factors is that for the fixed factors, you determined what your levels are and you measure all of them. So like in our condition, we decide there will be four conditions. For a random factor, it can be an additional factor which has many levels, and we did not measure all of those levels. So for example, if you're looking at, let's say, accountants' performance in 5 different companies, and you want to see if there is a difference whether they had a training or they did not have a training, how it affects their performance. So because you're interested in the factor of training, having training or not having training, or having different types of training, depends on your research, but you're less interested in whether they came from 5 different companies. Plus, 5 different companies were randomly chosen from, let's say, a pool of possible companies that could participate in this research. So the 5 companies would be 5 levels of a company factor, and they would be random, and therefore you'll put them in a random factor. However, most of the time, if you're not interested really in a factor like a company, you just would not include it in your data analysis altogether. So here we go. We have the same options. Again, descriptive statistic option. We choose homogeneity tests option. You can choose estimate of effect size. So that is quite important when you interpret your data. So we'll continue, nothing else we need, because this will just clutter our analysis and would not give us essential information that this task particularly requires. Those other options are useful if you're particularly looking for something else, but just a simple difference between 2 conditions. Post hoc tests, again, if you put condition in here, it will let you to choose which tests you want to do, just like in Oneway ANOVA, but we're not interested in post hoc at the moment. Plots, so the same, you can plot your factors, and usually if you have 1 factor, it will go on the horizontal axis. If you have 2 factors, you will present it by separate lines. So 1 factor will go on the horizontal axis, and another factor will be presented by separate lines, which basically not the factor, the levels of the factor will be presented by separate lines. If you have 3 factors, you can also, because it's a 2-dimensional graph, you'll have to split your plots into several plots, and each plot will correspond to yet another factor. If it's a bit too complicated, don't bother about it. It will come to you with practice and playing around. So we add our condition, simple, on a horizontal axis, continue. Nothing else we really need from here. Okay, and this is the output we'll get. It's exactly the same as for Oneway ANOVA with regards to the numbers, but the tables look slightly different. So for instance, descriptive statistic table look much simpler. It has your means, standard deviations, number of participants. It doesn't have all the confidence intervals for the means or minimums and maximums. We have our Levene's test, equality of error variances. So and it's not significant, so we're really happy. Our assumptions of our variances in each condition are equal is assumed. Between test effects, that's where you'll find the results or for your ANOVA, and condition will respond to your main effect for your factor condition, and it's basically tests if there is a difference between 4 levels of your factor. And here we get the F value and the significance level that are exactly the same as in Oneway ANOVA, but here we have error term, which corresponds to within participants measure in Oneway ANOVA. So in here we have error term with 20 degrees of freedom and mean square 21.3, and if we'll look at our Oneway ANOVA, we have within groups again with 20 degrees of freedom 21.3. So those values are exactly the same, and we get exactly the same plot for our means. So it's very straightforward. So this is the analysis with 1 factor. In the lecture we also covered the analysis of variance if you have two independent factors. So we don't have a data set for that, so if you want to rerun the analysis, you just create your own data set. But here's basically how the data set looks. So two-factor design, two-way ANOVA, and this is 2x3 ANOVA, which means 2 corresponds to 2 levels of factor title, and 3 would correspond to 3 levels of a factor text. So we would actually record it like 2x3 ANOVA. Oi, gosh, I'm saying 2x3 and typing 3x3. 2x3 ANOVA. Yeah, you can say 3x2, doesn't make any difference whatsoever. So you basically can create your own data file by opening your SPSS file, new data, and it will open for you a new window, and you just manually type in the data from your lecture slides. I cheated a little bit in here and I put them in Excel format, and now I can just copy paste them into my SPSS. It's very friendly with Excel, so if you have any data in Excel, there is no problem in transporting it into SPSS file. So here we have first, our variable is the dependent variable, and then we have two factors. Let me actually tell you what that data corresponds to. So from our lecture slides, this example is referring to a study to investigate participants' recall for different prose passages. 3 different pieces of prose, approximately the same length, were used. In addition, each passage was presented with and without accompanying title. 30 participants took part in the study, with 5 participants under each condition. Each participant was presented with the prose passage and subsequently asked to recall as much of the information as possible. Participants' recall was scored out of maximum possible 35 items for each condition. So we have our factor text, 3 texts, and factor title with the title or without the title. So because I wrote it in Excel, I remember which of the variables correspond to what, so I just need to assign them the names and the values. So this one, the first variable we know is our dependent variable, so, and dependent variable will be score. When you give the name to your variable, don't leave any spaces. SPSS does not like spaces in the variable name. It just simply would not record the name of your variable. Now the second one, I believe I gave it 1, 2, 3. Yeah, that corresponds to text. Oops, sorry. Variable view, so that would be our factor text. And here we can assign it values. So we can give 1 to text1 add, 2 to text2 add, and 3 to text3 add. Okay, and this last variable will be title or no title, so we'll just call it title, and we assign it values as 1 having a title and 2 having no title. In the labels, spaces don't matter. It's just in the variable names that SPSS doesn't like spaces. Recording your values is very beneficial because sometimes we create data set and we give it numbers a couple of weeks and we forget what we coded. So by going to values, you can always see what numbers correspond to what. So, and in here in the measures, our score is the scale variable, And then our text and our title are nominal variables. They basically correspond to which group a participant belonged to. So here we have 30 scores, text 1, so participant 1 scored 13, text 1, and the text was with the title. Participant 9 scored 14 on the first text, but he had no title. To transfer your numbers into labels for the variables, you can just press this 1A. It does the transformation for you, assuming that you recorded your values correctly. So, to do analysis with the two factors, you can only do that through the general linear model option. You go to univariate, and here you put your score in your dependent variable, title and text you put in the fixed factors, because we determined how many texts we'll give, and we determined whether they'll have title or not having title. So that's always a research designed to their fixed factors. We're going to options, and as usually choosing descriptive statistics, effect size, homogeneity tests, continuum, plots. Because with two factors, ANOVA will test the interaction, and this is one of the reasons why you would want to run two-way analysis of variance rather than just simply two-way, 2 times one-way ANOVA. It's because you want to see if there is interaction between text and title. So I usually advise people to put the factor with the most level on the horizontal axis. It's just easier to interpret data that way. But it doesn't matter which variable you put where. You can also select several graphs. You can ask SPSS to draw as many graphs as you want. It doesn't make any difference. It just depends which ones of them will be more useful for interpreting the interaction. So, horizontal axis text, it has 3 levels. Title has only 2 levels, we'll present by separate lines. We add that graph, text and title, continue, and I believe we don't need anything else. Okay, there we go. Univariate analysis of variance for 2 factors, text and title, tells us what they are, what the value labels, what are the numbers corresponding to, and what the number of participants in each condition. So like in text 1 we had 10 participants, out of who 5 had a title and 5 did not have a title. In the title, overall we had 15 participants, which means with the title there were 5 participants at each text level. So very simple really. Here in descriptive statistics it tells you with text 1, title 5, no title 5. So, and text 3, 5, 5, in total 10. So it basically gives you the same information, and it gives you means and standard deviations. So means and standard deviation will be important for interpreting your results. Here we go, Levine's test, we are very happy, it's not significant. And here is our main output. The main effect of text is not significant. Yeah. So, depending which text you were given, it doesn't have any mean differences on your recall score. So basically, the recall you had at each of the texts are not different from each other in groups. I think I'm not saying it really clearly, but basically the main effect of text that people in text 1 do not perform significantly different from people in text 2 and in text 3. So there was no difference between the 3 text groups. Now, with the main effect of title, we have a significant result, which means whether they had a title or did not have a title, their performance was significantly different. And we can look at the mean table to understand what's happening. So if we look at the total with the title, we have a mean of 24 out of possible 35, and with no title we only have a mean of 19. So basically the main effect of title tells you that 24 is significantly different from 19. So people who were given a title performed significantly better than people who were not given a title. Here also, text and title interaction, we have a significant interaction between the two. So what does a significant interaction means? It's you can look at the descriptive statistics and see how the interaction looks like, or if you asked for the plots, here is your interaction plot. So here you can see that in text 1, having a title or not having a title, the means were quite different. However, in text 2, they were actually the same. So for text 2, presence of the title did not have any effect on the recall. And in text 3, we can also see that the presence of the title had a significant impact on the number of on the quantity of information participants recalled. So, and this is basically the interaction one. Depending on the text, title either mattered or did not matter. So for text 1 and text 3, title result in significant improvement in the recall, and for text 2, having title or not having title, participants still performed rather poorly on recall. So, I believe that is it for our unrelated ANOVA. Well, try it out, play around with the data, and yeah, get used to looking at this output, but it's very straightforward. So, okay.